Here is another question regarding for the assignment number 8, problem 2517. You're given 3 figures and we're given the direction of the magnetic field. Ask you to find the direction and magnitude of induced current. So basically in the 3 figures, we're gonna use 2 or 3 formulas straightforward. And the questions here regarding for the direction. So the first formula that we use, the flux, which we base it in the area magnitude field and cosine theta. That's the first one. And the second one, we use the induced EMF, the equation of the induced EMF, the rate of the flux. If I have in tail, so this is when the area of the flux, delta phi divided by delta t. Once you find the induced flux, induced EMF, you can find induced current. So induced current Ohm's law, we're gonna be induced EMF times R. So in 3 problem, we're gonna apply 3 formulas. So we're gonna use Lenz's law and Faraday's law. So Lenz's law to identify the direction of electrical current. And then we're gonna use the Faraday's law to find the magnitude of the or induced EMF. So since this equation is here regarding for the directions, I just find the direction for everything. So let's start from the figure A. In the figure A here, we're given the magnetic field point out of the page and with the 0.5 Tesla per second, the flux. Sorry. And this flux here increasing, which basically perpendicular with the magnetic field. So magnetic field increase as well. According for the Lenz's law, to prevent that increase, the loop should be generate a magnetic field to prevent that. So in opposite direction. So we're gonna prevent. So right now, when I'm talking about the induced EMF, it's based in the induced magnetic field. So we find the direction of the current. What we're gonna use, we're gonna use the right hand rules. So right now, my magnetic field point into the page, and I need to find my current, which is clockwise or counterclockwise. Here's a quick reminder for the right hand rules with exactly the same scenario that we have right now. The magnetic field point in, so we're gonna put my fingers to the page and my thumb will be toward the current. So from here, the current will be clockwise. So here's the clockwise directions for this particular case. Clockwise direction. So let's move for the B. And then when you find, you have given the odd information, you can find and use it. Let's go for the second one, which I think that's the question regarding for one. So here we have the flux, the flux is 0.5 Tesla per second, and my magnetic field decrease. Again, we have to start from the Lenz's law. Lenz's law, if that case, the magnetic field decrease, the Lenz's law stated that should be try to keep it constant. So in that case, you're gonna generate induced magnetic field to support that magnetic field. So we're gonna generate induced magnetic field. It should be point to the page. So the question is here, because the magnetic field or the induced magnetic field that generates from the loop, just to keep it constant since the magnetic field decrease, so I generate a induced magnetic field point to the page as well. So similarly, how to directions, we're gonna go to the right hand loop, right hand rules, but I have the same case that we have right now. So in that case, definitely I will see the same answer, counterclockwise. So this, regarding this questions here, that's why. So magnetic field point to the page, right hand rules, the induced current will be clockwise. The last one here, the only for the first and second case we have here is the theta is 0 degree. Okay, so they are the same. So but here in the second and the third one here, we have to find a theta, which is the angle between the center of the wires and magnetic field. So here is the center of the wire and magnetic field point to the page. So I have, here is the theta will be 90 degree. So from 90 degree, I have no flux, I have no EMF, I have no induced current. Okay. I hope that helped the question to identify the direction of induced magnetic field. Thank you so much.